Picture a world on fire, a planet bleeding molten rock for more than 1,000,000 years straight. This wasn't a brief, violent explosion. It was a slow, relentless hemorrhage of lava that poured from deep within the Earth, reshaping continents, choking the skies, and pushing life itself to the very edge of extinction. 252 million years ago, our planet experienced one of the most catastrophic events in its history, an era of unimaginable volcanic fury that scientists now call the Great Dying. It was a chapter so extreme, so devastating, that it forever altered the course of evolution and left scars on the Earth that we're still learning to read today. What's truly astonishing is that this wasn't just some ancient disaster locked away in the distant past. The clues are all around us, etched into stone, buried in layers of rock, and preserved in the fossils of creatures that barely survived. This is a detective story written in lava and limestone, a mystery that geologists, paleontologists, and climate scientists have been piecing together for decades. And what they've uncovered is more incredible than anything we could have imagined. A tale of epic forces, fragile ecosystems, and a planet pushed to its absolute limits. So today, we're going to journey back in time to witness this planetary inferno. We'll explore how it happened, what it did to the world, and how life somehow found a way to endure. We'll look at the evidence, the chemical fingerprints in ancient rocks, the silent stories told by fossilized bones, and the subtle traces of gas that poisoned an entire atmosphere. This isn't just a story about destruction, it's about resilience, curiosity, and the enduring quest to understand our planet's deepest secrets. By the end, you'll see the world a little differently, and you might just recognize how these ancient echoes still shape the Earth we call home today. To truly grasp the enormity of what was about to unfold, we must first step back into the world as it existed just before the cataclysm. This was the Permian period, a fascinating and dynamic chapter in Earth's history that stretched from around 299 to 252 million years ago. The planet looked almost unrecognizable compared to today. Instead of the familiar continents we know, nearly all of the world's landmass was fused into one colossal supercontinent known as Pangea. This immense landform stretched from pole to pole, a vast, uninterrupted expanse of deserts, inland seas, and sprawling forests of primitive conifers and ferns. With so much territory connected, life was able to spread and diversify in remarkable ways, creating ecosystems that were both strange and magnificent. On land, the Permian was dominated by an incredible array of early reptiles and the ancestors of mammals, creatures known as synapsids. These were not the dinosaurs we so often picture; those would come much later. This was the age of animals like Dimetrodon, with its iconic sail-like back fin, and the heavily armored Scutosaurus. The world buzzed with the clicks and scuttles of giant insects, while the skies were still the exclusive domain of winged reptiles yet to evolve. In the oceans, reefs built by brachiopods, corals, and crinoids thrived in shallow seas, supporting a complex web of marine life that included ancient sharks, ammonoids with their coiled shells, and a plethora of fish species. The climate, though generally warmer than today and marked by pronounced seasons across the giant continent, had reached a state of relative stability. This period of environmental equilibrium allowed life to flourish, reaching a peak of biodiversity that the planet had never seen before. Yet beneath this surface of thriving life and continental grandeur, immense geological forces were gathering strength. The very formation of Pangea, a process of continents colliding and welding together over millions of years, had profound consequences. All that tectonic pressure had to go somewhere. The planet's crust was like a tightly coiled spring, storing enormous energy deep beneath the surface, particularly under the region we now know as Siberia. The Earth's mantle was growing restless. A colossal upwelling of superheated rock, a mantle plume, was slowly rising from the boundary between the core and the mantle. This plume was generating unimaginable heat and pressure, silently weakening the lithosphere above it. The stage was being set not for a simple volcanic eruption, but for a planetary-scale event. The Permian world, in all its rugged beauty and biological brilliance, was unknowingly sitting directly above a fuse that was about to be lit, a fuse connected to enough pent-up volcanic force to nearly end the story of life itself. This peaceful, stable period was the calm before the most violent storm in Earth's history. But this stability was about to shatter in the most dramatic way imaginable, as the geological fuse lit beneath Siberia reached its breaking point. The stage was now set for the main event, a volcanic cataclysm so immense it defies easy comprehension. This is where our story truly ignites, at a place known as the Siberian Traps. Picture an area of volcanic rock so vast it covers over 2 million square miles. That's an expanse larger than all of Western Europe. This is not a single, cone-shaped volcano like we might imagine today, but something far more terrifying and powerful. It's a colossal province of flood basalts, a landscape utterly drowned under layer upon layer of solidified lava, each flow a testament to a separate, devastating eruption. The name Traps itself comes from the Swedish word for stairs, and if you were to look at this region from the ground, you'd see exactly why. Over millennia, these successive lava flows cooled, contracted, and cracked, creating a dramatic stair-step topography that scars the land to this very day. The sheer volume of material released here is almost beyond human scale. We're talking about millions of cubic miles of magma surging up from the Earth's mantle, flooding across the ancient Siberian landscape. This wasn't a quick, explosive event over in a few days. This was a planetary hemorrhage that persisted, on and off, for close to 1 million years. Try to fathom that timescale, a continuous, simmering eruption that would have made the entire region an uninhabitable hellscape of molten rock and poisonous fumes for thousands of consecutive human lifetimes. Each new pulse of lava would have spread out like a tidal wave of fire, incinerating everything in its path and burying the land under hundreds of feet of new rock, only for the process to repeat again and again after a brief period of cooling. And it wasn't just the lava itself that made this event so catastrophic. With each eruption, unimaginable quantities of gases and fine ash were launched high into the atmosphere. These weren't minor emissions. We're talking about trillions of tons of carbon dioxide, sulfur dioxide, methane, and halocarbons being pumped directly into the air, creating a toxic, planet-altering cocktail. The Siberian Traps became the epicenter of the entire Permian-Triassic crisis, the ground zero for a chain reaction that would eventually envelop the entire globe. The immense physical size of this volcanic province is the first and most obvious clue geologists have, a visible testament to the sheer magnitude of the forces unleashed. It's the starting point for the entire mystery, the undeniable evidence that something truly apocalyptic happened here, and its story is written in every step of that dark volcanic rock. But what could possibly fuel such a sustained and devastating release of volcanic energy? The answer lies deep beneath the surface, in the powerful and restless movements of the Earth itself. The trigger for this million-year-long catastrophe is believed to have been a massive mantle plume, a colossal upwelling of superheated rock originating from the very boundary between Earth's core and mantle. Think of it as a gigantic, slow-moving bubble of intensely hot material, rising through the planet's interior like a blobs in a lava lamp, only on an unimaginably vast scale. This plume had been traveling upwards for millions of years, carrying with it immense thermal energy from the core. When it finally reached the base of the lithosphere, the rigid outer shell of the planet beneath Siberia, it didn't just gently arrive, it slammed into it with catastrophic force. The effect was like holding a blowtorch to the base of a thick sheet of ice. The intense heat from the plume began to melt the overlying rock, creating a massive reservoir of magma just below the surface, a seething chamber of molten fury. But heat alone wasn't the only force at work. The sheer physical pressure exerted by the rising plume began to dome the crust upwards, creating vast fissures and fractures in the suddenly brittle lithosphere. This process, known as rifting, essentially cracked the Earth's shell open. These fractures became the perfect conduits, the release valves for all that pent-up magma. It wasn't a single volcanic vent that formed, but a series of gigantic cracks in the planet's surface, stretching for hundreds of miles, from which floods of lava poured forth continuously. Some fascinating theories suggest this mantle plume didn't act alone. It may have encountered a perfect storm of pre-existing weaknesses in the Siberian crust. The region could have been crisscrossed by ancient fault lines or been near a subduction zone, where one tectonic plate was already sliding beneath another. The rising plume would have exploited these weaknesses, amplifying its destructive potential. It's the geological equivalent of pushing on a door that's already slightly ajar. The existing cracks made it exponentially easier for the immense pressure from below to burst through. This combination of a deep-seated thermal anomaly and a fragile, pre-stressed crust provides the critical insight into how such a prolonged and voluminous volcanic event was not just possible, but perhaps inevitable given the right subterranean conditions. The stage was set not by a single cause, but by a confluence of deep Earth dynamics that came together to create the most destructive volcanic episode our planet has ever witnessed. The eruption of the Siberian Traps wasn't a single, continuous explosion, but a relentless, pulsating deluge of molten rock that defined an entire geological epoch. Imagine a cycle of unimaginable violence repeating itself over and over across millennia. Each individual pulse began with the ground itself splitting open along fissures that could stretch for hundreds of miles. From these colossal wounds in the planet's crust, lava of a specific type called flood basalt would pour forth. This wasn't the thick, viscous lava we see oozing from volcanoes like Hawaii's. This was a far more fluid and fast-moving torrent, spreading across the ancient Siberian landscape like a tidal wave of fire. A single one of these flows could cover an area the size of a small country, moving at speeds that would have made escape impossible for any creature in its path. As it advanced, it would have incinerated everything: forests, soil, even entire river systems, instantly turning a living world into a barren plain of black rock. The sheer scale of each event is difficult to overstate. When one of these massive flows finally cooled and solidified, it left behind a layer of basalt rock that could be hundreds of feet thick. To put that in perspective, that's the height of a 20-story building, all formed from a single catastrophic outpouring of magma. And then, after a period that might have lasted centuries or even a few millennia, the cycle would begin again. The landscape would get a brief, eerie respite. In these quieter intervals, a thin layer of soil might start to form from wind-blown dust, or a shallow lake could pool in the low spots of the rugged, newly formed rock. Perhaps a few hardy plants would take root, and the first brave pioneer species of animals might wander back into the devastated region, but this fragile recovery was always temporary. It was merely the calm between storms. Without warning, the Earth would fracture again in a new location, and another unimaginable volume of lava would flood out, utterly burying any signs of that brief life under a fresh, searing hot layer of rock hundreds of feet deep. This stop-start pattern of destruction is precisely what created the iconic stair-step topography, the traps, that gives the region its name, each new flow stacked upon the last, building a geological layer cake of catastrophe that today is over 2 miles thick in some places. The duration of this entire eruptive sequence, lasting for nearly 1 million years, is one of the most critical clues scientists have. It tells us that the environmental damage wasn't a single, sharp shock to the global system, but a prolonged and escalating assault. The planet wasn't just hit once, it was subjected to a relentless beating, with each new pulse of lava injecting more heat into the atmosphere, and each period of quietude being too brief for ecosystems to truly recover. This intermittent but utterly relentless nature of the flows meant that Earth's life support systems were pushed past a point of no return, not by one disaster, but by 1 million years of repeated trauma. The stacked basalt layers are therefore more than just rock. They are the pages of a calendar counting down to the greatest extinction event of all time. While the lava flows were a terrifying spectacle of raw geological power, the true architects of the global catastrophe were invisible. The eruptions did far more than just pour molten rock across Siberia. They acted as massive exhaust pipes for the planet, spewing colossal quantities of volatile gases directly into the atmosphere. Imagine each of those fissures stretching for miles, acting like a poorly tuned engine running at maximum capacity for centuries on end. The primary exhaust was carbon dioxide, a potent greenhouse gas, released in volumes that dwarf anything human industry has ever produced. Current estimates suggest the Siberian Traps may have released upwards of 100,000 gigatons of carbon dioxide over that million-year period. To put that almost incomprehensible number into perspective, it's more than 40 times the total amount of CO2 that would be released if we burned every single fossil fuel reserve on Earth today. But CO2 was just one component of this poisonous cocktail. The eruptions also released staggering amounts of sulfur dioxide, a gas that has a much more immediate and sinister effect. In the upper atmosphere, SO2 reacts with water vapor to form sulfuric acid aerosols, creating a pervasive veil that first reflected sunlight back into space, potentially causing a brief period of global cooling. However, this acidic haze soon fell back to Earth as relentless, corrosive acid rain. This wasn't just a light drizzle, it was rain as acidic as undiluted lemon juice, falling across the entire planet for thousands of years. It would have scorched vegetation, leached essential nutrients from soils, and turned freshwater lakes and rivers into toxic, lifeless broths, devastating both terrestrial and aquatic ecosystems. Perhaps most dangerously, the volcanic activity released vast clouds of halocarbons, chlorine and fluorine-based compounds that rose high into the stratosphere. There, they initiated a chemical chain reaction that chewed through the ozone layer, Earth's essential protective shield against the sun's harmful ultraviolet radiation. With this shield severely depleted, the planet's surface was bathed in mutagenic UVB rays, causing widespread damage to plant life, harming the photosynthetic plankton that form the base of the marine food web, and increasing cancer and mutation rates in animals. The combination of extreme greenhouse warming from CO2 and methane, surface poisoning from acid rain, and DNA damage from ultraviolet radiation created a triple threat that attacked life on every front. This atmospheric poisoning, whose chemical fingerprints are still preserved in ancient rocks, is the most compelling clue linking the Siberian volcanism directly to the global biological collapse that followed. The lava was a local disaster, but the gases were a planetary one. This dramatic shift in the atmosphere's composition didn't just tweak the global thermostat. It completely rewired the planet's entire climate system, flipping it from one stable state into another with terrifying speed. To truly understand the scale of this change, we need to picture the pre-eruption world. For millions of years during the late Permian, Earth had been in what climatologists call an icehouse state. This doesn't mean the planet was a frozen snowball, but rather that it had significant and permanent ice caps at both poles, much like today. These great white reflectors at the top and bottom of the world played a crucial role in regulating the global climate, bouncing a substantial amount of solar energy back into space and helping to maintain a cooler, more stable temperature gradient from the equator to the poles. Ocean currents, driven by the temperature difference between the cold poles and warm tropics, circulated nutrients and oxygen, supporting rich marine ecosystems. On land, the large supercontinent of Pangea had its own distinct seasonal patterns, but overall, the climate was manageable and predictable for the life that had adapted to it over eons. Then the gases arrived. The colossal and continuous volcanic emissions acted like slamming your foot on the accelerator of Earth's climate system, hurtling it from that stable icehouse directly into a searing greenhouse state. The trillions of tons of carbon dioxide and methane created an incredibly thick atmospheric blanket, trapping the sun's heat with devastating efficiency. Geological evidence, particularly from the analysis of oxygen isotopes in the fossilized shells of tiny marine organisms called foraminifera, tells us that average global temperatures skyrocketed. We're not talking about a minor fluctuation of a degree or two. Current estimates point to a global average temperature increase of around 8 to 10 degrees Celsius in a remarkably short geological time frame, perhaps as little as a few tens of thousands of years. To put that into a modern perspective, that's more than 10 times the amount of warming our planet has experienced since the last ice age ended, and it happened at a pace that would have been utterly catastrophic for life. The effects of this superheating were immediate and catastrophic on a planetary scale. The first and most obvious casualty was the polar ice. Those massive ice caps, which had been a permanent feature for so long, simply melted away. This wasn't a slow retreat, it was a rapid collapse, pouring enormous volumes of freshwater into the oceans. The result was a dramatic rise in sea level, estimated to be tens of meters higher than before, which would have drowned vast stretches of coastal ecosystems and shallow marine continental shelves that were hotspots of biodiversity. But the melting ice did more than just raise sea levels. It fundamentally broke the engine of the ocean, the global conveyor belt of ocean currents, which relies on dense, cold, salty water sinking at the poles to drive deep water circulation, began to falter and then stall entirely. With no cold polar water to sink, the great ocean conveyor system ground to a halt. This collapse of ocean circulation had a domino effect that rippled across the entire planet. Weather patterns, which are intimately tied to both ocean currents and temperature gradients, went haywire. The once predictable monsoon systems likely failed or shifted dramatically, turning lush coastal regions into deserts and flooding arid interiors with unpredictable rains. The loss of the temperature difference between the poles and the equator weakened the jet streams, leading to more stagnant and extreme weather conditions. On land, continents that were already arid became scorching hot deserts, while tropical regions became almost uninhabitably hot and humid. The evidence for all of this chaos is meticulously recorded in the rocks themselves. Geologists can read this ancient story in the layers of sediment, the sudden disappearance of glacial deposits, the chemical signatures in ancient soils that indicate extreme aridity, and the changes in fossilized plant pollen that reveal a dramatic shift in vegetation patterns. These silent stone pages tell a unanimous story of a climate system pushed past its breaking point, a world that was fundamentally and violently remade by the volcanic fumes that choked its skies. While the atmosphere was being choked and the climate was spinning out of control, a quieter, more insidious killer was at work in the world's oceans, one that would prove just as devastating to life. A huge portion of that immense volume of carbon dioxide being pumped into the air didn't stay there. It began to dissolve directly into the seawater. The ocean, in its vastness, acts as a massive sponge for this gas, and over that million-year period, it was forced to absorb trillions of tons of it. This process triggered a fundamental chemical change in the water itself, a shift in its very pH balance. The seas, which had been slightly alkaline for eons, began a slow, steady slide toward acidity. This wasn't a sudden, dramatic change like a science experiment with vinegar and baking soda, but a relentless, pervasive alteration of the entire marine environment on a global scale. It was a silent, invisible crisis unfolding beneath the waves, and for the creatures that called the ocean home, it was absolutely catastrophic. The victims of this chemical assault were the countless marine organisms that built their shells, skeletons, and hard external structures out of calcium carbonate. For these creatures, the slightly alkaline ocean had always been a perfect construction site. The chemical conditions allowed them to easily extract calcium and carbonate ions from the water and cement them together into strong, protective armor. But as the ocean became more acidic, that fundamental chemistry was turned upside down. The excess CO2 reacting with seawater creates carbonic acid, which in turn releases hydrogen ions. Those hydrogen ions aggressively seek out and bond with the available carbonate ions, effectively stealing the very building blocks these animals needed to grow and maintain their shells. It's the equivalent of trying to build a brick wall in a town where someone is constantly following behind you, pulling the mortar out from between your bricks. The process of shell formation became incredibly difficult, energetically expensive, and for many species ultimately impossible. We can see the devastating impact of this by looking at the most crucial members of the marine ecosystem first, the tiny, floating plankton. Species like foraminifera and coccolithophores are microscopic algae that are encased in intricate and beautiful calcium carbonate shells. Individually, they are tiny, but collectively, they form the foundational base of the entire marine food web. Countless fish, shrimp, and even giant whales depend on these minuscule creatures for food. Furthermore, through photosynthesis, they produce a significant portion of the world's oxygen. As the acidic water made it harder for them to form their shells, their populations began to crash dramatically. Their loss created a double catastrophe. It ripped the first and most important rung out of the marine food ladder, and it also reduced the ocean's capacity to draw down CO2 from the atmosphere, creating a vicious feedback loop that accelerated the warming. The devastation didn't stop at the base of the food chain. It radiated outward, affecting every shell-building creature in the sea. Vast reefs, which were not built by modern corals but by now extinct organisms like rugose and tabulate corals, along with massive colonies of sea sponges, began to literally dissolve away. These complex underwater cities, which provided habitat, breeding grounds, and protection for thousands of other species, crumbled into rubble. On the seafloor, mollusks like clams and snails, and brachiopods, which look like clams but are a completely different phylum, struggled to grow their protective homes. Their shells became thin, brittle, and malformed, leaving them vulnerable to predators and disease. Ammonoids, free-swimming cephalopods with their iconic coiled shells, also faced this existential threat. The collapse of these groups wasn't just a loss of biodiversity. It was the systematic dismantling of entire marine ecosystems from the bottom to the top. The most compelling and undeniable evidence for this ancient acidification event is locked within the chemistry of the rocks themselves. Geologists can drill into deep-sea sedimentary layers that were deposited on the ocean floor during the end of the Permian period. When they analyze these rocks, they find a startling and consistent chemical signature. The layers that correspond with the extinction boundary show a dramatic drop in the proportion of carbonate material. It's as if someone suddenly turned off a tap. This makes perfect sense. With so few shell-building organisms left alive, far less carbonate material was raining down to the seafloor to become rock. Furthermore, careful analysis of the isotopes of boron, an element whose behavior in seawater is directly tied to pH, confirms a sharp and sustained spike in acidity right at this time. These chemical clues, silent and immutable, form an indisputable record of a global ocean that became suddenly and lethally hostile to its inhabitants, a direct consequence of the volcanic gases that had poisoned the world above. Even as the oceans grew warmer and more acidic, another lethal threat was silently spreading through the world's waters, one that would prove to be the final blow for countless marine species. This was the rise of anoxia, a catastrophic drop in dissolved oxygen levels that effectively suffocated the seas from within. The primary driver of this underwater crisis was once again the immense volume of volcanic gases. The same greenhouse effect that was superheating the atmosphere also had a devastating impact on the oceans. Warmer water simply cannot hold as much dissolved oxygen as cooler water, much like a warm soda goes flat faster than a cold one. As global temperatures soared, the ocean's capacity to retain life-giving oxygen diminished significantly, creating a widespread and fundamental stressor for all marine life that relies on gills to breathe. But the warming was only part of the story. The stagnant, oxygen-starved conditions were dramatically worsened by a sinister feedback loop. On land, the relentless acid rain was chemically burning away vegetation and stripping the soil bare. With no roots to hold it in place, this barren landscape began to erode at an unprecedented rate. Torrential rains, likely from the disrupted weather patterns, washed incredible amounts of this eroded soil and dissolved nutrients into the rivers and ultimately into the oceans. This nutrient-rich runoff acted like a massive overdose of fertilizer for the microscopic algae floating in the surface waters. It triggered colossal, perpetual algal blooms that spread across the ocean surfaces like a thick, green scum. While these tiny organisms photosynthesize and produce oxygen during the day, their sheer overwhelming numbers create a different problem entirely. When they die, they sink into the darker, deeper water where bacteria get to work decomposing them. This process of decomposition consumes enormous amounts of oxygen, effectively respiring it away from the water column and creating vast expanses of water where breathing is impossible. The result was the creation of enormous dead zones, deep water realms where oxygen levels plummeted to near zero. These were not small, isolated areas. Geological evidence suggests they expanded to cover most of the world's ocean basins, from the depths all the way up to the shallows in many regions. For the animals living there, this was a death sentence. Oxygen-breathing creatures from the smallest shrimp to the largest predatory fish would have faced agonizing suffocation. Their options were grim: flee to the dwindling oxygen-rich areas near the surface or perish. This massive compression of habitable space into a thin, warm surface layer created fierce competition and stress. further weakening ecosystems already on the brink from acidification and warming. The combination of heat, acid, and now suffocation formed a trio of interlinked killers that left marine life with nowhere to hide. The proof of this global suffocation is permanently etched into the stone record. When geologists examine sedimentary rocks laid down on the ancient seafloor during the extinction, they find two very telling types of layers. First, there are thick deposits of black, organic, rich shale. This dark rock is packed with the undecayed remains of all that organic matter, the dead algae and other plankton, that settled to the bottom but could not fully decompose because the bacteria responsible for breakdown were also starved of oxygen. This preserved organic sludge is a direct signature of an oxygen-deprived environment. Even more revealing is the presence of the mineral pyrite, also known as fool's gold. Pyrite forms in sediments only under strictly anoxic conditions, when certain bacteria that breathe sulfate instead of oxygen metabolize organic matter and produce hydrogen sulfide as a toxic waste product. This hydrogen sulfide then reacts with iron in the water to form pyrite crystals. Finding widespread layers of pyrite-rich rock from this time period is like finding the chemical fingerprint of a stagnant, suffocated ocean. Together, this evidence paints an undeniable picture of seas that were not just warmer or more acidic, but were fundamentally stripped of the very element most complex life needs to survive, completing a recipe for ecological collapse that few species could withstand. This convergence of environmental disasters created a perfect storm of extinction, a biological catastrophe so complete it is almost beyond our comprehension. We call it the Permian-Triassic extinction event, but that clinical name belies its true horror. It has earned a far more fitting and grim moniker, the Great Dying. The numbers alone are staggering, representing a loss of life on a scale the planet has never seen before or since. In the oceans, up to 96% of all marine species vanished forever. Picture the vibrant reefs, the schools of strange fish, the drifting ammonoids, almost all of them gone. On land, the devastation was nearly as severe, with an estimated 70% of terrestrial vertebrate families disappearing from the fossil record. This wasn't just a bad day for life on Earth, it was a near-total erasure. The collapse wasn't isolated to a single habitat or region, it was a synchronized global failure. On land, the lush forests of conifers and ferns that had covered Pangea were decimated by the combination of acid rain, ozone depletion, and brutal temperature shifts. The fossilized pollen record shows a dramatic shift from diverse plant spores to a world dominated by a single, hardy type of fungus, an organism that thrives on decay and death, painting a vivid picture of a landscape carpeted in rotting vegetation. The rivers and lakes, poisoned by acid rain and choked with eroding sediment, became lifeless. In the oceans, the collapse was even more absolute. The intricate food webs that depended on shell-building organisms and photosynthetic plankton disintegrated from the base upwards. The great reefs, which had been thriving for millions of years, did not just die, they stopped being built altogether, leaving a gap in the geological record that lasts for millions of years. The deep basins became silent, oxygen-starved graveyards. What makes the Great Dying so uniquely terrifying in the history of life is not just the scale of death, but the profound lack of survivors. This wasn't an event where the generalists, the adaptable creatures, made it through. Entire branches of the tree of life were lopped off completely. In the sea, whole classes of animals, like the trilobites that had survived for hundreds of millions of years, were finally finished off. The once dominant brachiopods were pushed to the brink, never to recover their former glory, while their ecological place was taken by mollusks like clams and snails. On land, the magnificent and diverse synapsids, the ancestors of mammals, were absolutely devastated. Huge, lumbering herbivores and formidable predators alike disappeared, their reign ended. The few survivors were a scrappy, desperate bunch. They were often small, burrowing animals or creatures that could tolerate low oxygen environments, or those with generalist diets that could eat whatever scraps remained. They were the lucky few, but they inherited a world that was utterly broken. This biological carnage is the single most profound clue linking the volcanic activity in Siberia directly to a global catastrophe. The timing is perfect. The most intense pulses of eruption align exactly with the sharpest drop in biodiversity seen in the rocks. The pattern of extinction makes perfect sense given the environmental drivers. Shell-building creatures were hit hardest by acidification. Large active animals suffered most from oxygen deprivation, and everything struggled with the soaring temperatures and food scarcity. The fossil record doesn't show a neat, single layer of death. Instead, it reveals a protracted struggle, a series of pulses of extinction over tens of thousands of years that correspond with successive waves of volcanic activity. Life didn't end with a single bang, but with a long, agonizing whimper, repeatedly knocked down just as it tried to get back up. This intimate connection between the volcanic fingerprints in the rock and the biological annihilation they caused provides the most compelling evidence we have that the story of the Siberian Traps is the story of the great dying itself. While the chemical and geological clues give us the framework of the catastrophe, it is the fossils that give this ancient tragedy its heart and soul, transforming abstract data into a visceral story of life and death. These preserved remains act as a direct window into that dying world, offering a poignant, bone-by-bone account of the collapse. The most telling fossil beds are found in places that were once teeming with life, like the Karoo Basin in South Africa. Here, the rock layers tell a story in stark contrast. In the older strata from the late Permian, we find a breathtaking diversity of life. The fossils are abundant and varied. The skulls of powerful Gorgonopsians, saber-toothed apex predators that ruled the land. The heavy, barrel-shaped skeletons of Parasaurs, giant herbivores the size of small cars, and the delicate bones of smaller reptiles and early synapsids, all intermingled, painting a picture of a complex, thriving ecosystem. It was a world of giants and specialists, each creature perfectly adapted to its niche in a stable environment. Then you reach the boundary layer. In a geological instant, that vibrant world vanishes. The rock changes color and texture, often marked by a layer of ash or sediment that settled in the aftermath of the initial eruptions. Immediately above this line, the fossil record becomes a ghost town. The giants are simply gone. No more Gorgonopsian skulls, no more massive Parasaurs. The incredible diversity of the Permian is replaced by a startling monotony. For a long period after the extinction, the most common fossil you find is a single, humble animal, Lystrosaurus. This dog-sized, burrowing herbivore with its turtle-like beak and two stubby tusks was never meant to be a star. Before the disaster, it was a minor player in a much larger cast, but its simple traits, its ability to dig burrows to escape the harsh surface conditions, its generalist diet that could handle tough, scorched vegetation, and its relatively small size requiring less food became the ultimate keys to survival. In the post-apocalyptic world, Lystrosaurus didn't just survive. It exploded across Pangea, making up as much as 95% of all land vertebrates in some fossil assemblages. Its sudden, overwhelming dominance is one of the most powerful pieces of evidence for the severity of the extinction. It wasn't that Lystrosaurus evolved to win, but that it was one of the only players left on the field. This same story of abrupt change is recorded in the rocks of Greenland, which in the Permian was nestled in the far north of Pangea. The fossilized remains of lush forests are abruptly sealed under layers of silt and sand that washed in from the now barren continents. We see a similar pattern in the marine record, from the mountains of Italy to the coasts of China. Layers of limestone packed with a kaleidoscope of fossilized shells, brachiopods, clams, ammonoids, and corals are suddenly capped by a dark, grim layer of shale that is almost completely barren. This layer, often just a few inches thick, represents millennia of silent, lifeless ocean floor, where the only thing settling was fine mud and the occasional carcass of a creature that somehow clung to life. Then, slowly, a few fossils reappear in the rocks above, but they are a pale imitation of what came before. The new species are smaller, less diverse, and often have thinner, more poorly formed shells, struggling in the still hostile environment. These fossil sequences do more than just date the event. They meticulously document the biological response, showing us which traits became liabilities and which, through sheer luck, became a lifeline. They tell us that the Great Dying was a brutal filter, and only the hardiest, most adaptable, and often most inconspicuous creatures made it through to the dawn of the Triassic. But to truly understand the scale of this atmospheric poisoning, we need to move beyond the visible evidence and into the realm of atomic-level detective work. This is where isotopic analysis comes in, a powerful scientific technique that allows geologists to read the chemistry of the catastrophe with astonishing precision. Think of elements not as single entities but as families. Many elements have different versions called isotopes, which are identical in their chemical behavior but have slightly different atomic weights. Carbon, for example, mostly comes as carbon-12, which is light, with a very small percentage being the slightly heavier carbon-13. Under normal conditions, the ratio of carbon-13 to carbon-12 in the atmosphere, oceans, and living things remains in a stable, predictable balance. Life itself actually prefers the lighter carbon-12 isotope, incorporating it more easily into organic matter. So, plants, animals, and the fossil fuels they eventually become are all naturally enriched with light carbon. When the Siberian Traps began their million-year eruption, they didn't just release any carbon, they released a specific, identifiable type. The magma from deep within the mantle is particularly rich in light carbon isotopes. As this colossal amount of volcanic CO2 flooded the atmosphere and then dissolved into the oceans, it dramatically shifted the global carbon cycle's balance. It was like pouring a giant bucket of light carbon into a carefully measured pool, drastically diluting the overall ratio of heavy carbon-13 to light carbon-12. This event left an indelible mark in the rock record. When geologists take samples of sedimentary rock from the end Permian boundary and analyze their carbon isotope ratios, they find a massive, sudden negative swing. This sharp drop in the proportion of carbon-13 is one of the most definitive chemical fingerprints of the entire event. It's not just a marker of change, it's a precise measure of the unimaginable volume of volcanic carbon that was injected into the system, confirming that the source was indeed a gargantuan geological event and not just a minor fluctuation. The story doesn't end with carbon. This same isotopic detective work extends to other elements, each adding another layer of confirmation to the narrative. Sulfur isotopes tell a particularly grim tale. Volcanic eruptions are a major source of sulfur dioxide, and the isotope ratios of sulfur in rocks from this time show another dramatic shift. This signature helps scientists track the spread of the toxic gas clouds and the resulting acid rain that scorched the planet. Furthermore, the widespread anoxia in the oceans, those vast suffocating dead zones, also left its own unique sulfur signal. Certain bacteria that thrive in oxygen-free environments process sulfur in a very distinctive way, leaving behind an isotopic signature that is unmistakable. Finding this signal in marine rocks from the extinction layer is like finding a chemical confession from the very microbes that flourished in the suffocated seas. Strontium isotopes offer yet another perspective, one that speaks to the sheer physical weathering of the continents. The relentless acid rain didn't just kill plants, it chemically ate away at the surface rocks of Pangea. This intense erosion would have washed huge amounts of sediment into the oceans, and this sediment has a specific strontium isotope ratio that differs from the strontium normally found in seawater from volcanic vents or hydrothermal systems. By analyzing the strontium in ancient marine limestone layers, geologists have detected a significant shift right at the Permian-Triassic boundary, pointing to a massive pulse of continental erosion caused by the acidic conditions. Together, these isotopic systems, carbon, sulfur, and strontium, form an interlocking set of evidence. They don't just tell us that something bad happened, they provide a detailed timeline and a quantified measure of the catastrophe. They tell us what was released, how much there was, and how it fundamentally altered the chemistry of the entire planet, from the highest atmosphere to the deepest ocean floor, offering some of the most conclusive proof of the link between the fires of Siberia and the death of a world. While the isotopic shifts in carbon and sulfur provide a broad chemical backdrop for the catastrophe, another element offers a much more direct and tangible link straight back to the volcanic vents themselves, Mercury. This volatile heavy metal acts like a geologic smoke gun, leaving an unambiguous fingerprint that points directly to the Siberian Traps as the culprit. Massive volcanic eruptions are among the largest natural sources of mercury emissions on Earth. When a volcano erupts, it doesn't just spew lava and common gases. It also releases a cocktail of volatile metals from the depths, and mercury is a key component. Because it's elemental and vaporizes easily at high temperatures, this mercury doesn't just fall nearby. It gets launched high into the atmosphere, where global wind systems can carry it across the entire planet before it eventually settles back to the surface, either falling directly onto the land or raining down into the oceans. Once it settles, this mercury becomes trapped. In marine environments, it sinks to the seafloor and gets buried in the layers of sediment that are slowly, continuously building up. There, isolated from the oxygen-rich water above, it can remain preserved for hundreds of millions of years, a silent, metallic time capsule waiting to be read. This is where the detective work begins. Geologists can drill deep into these ancient seabed rocks, extracting long, thin cores that act like a vertical timeline of Earth's history. They then carefully sample these cores, moving millimeter by millimeter through layers that represent millennia of deposition. Using incredibly sensitive instruments, they can measure the precise concentration of mercury in each tiny sample. What they've found at the Permian-Triassic boundary is nothing short of stunning. In rock layers from every corner of the globe, from the mountains of China to the cliffs of Greenland to the ancient seabeds now exposed in Canada, there is a massive, abrupt spike in mercury concentrations. This spike isn't just a minor blip, it's an anomaly that dwarfs the background levels found in the rocks above and below. It's a clear signal of a sudden, enormous, and global pulse of mercury pollution. The power of this mercury clue lies in its specificity. While other environmental changes like ocean anoxia or climate shifts can have multiple potential causes, a global mercury spike has one primary, unambiguous source: exceptionally large-scale volcanism. Other events like asteroid impacts can also release some mercury, but the pattern and scale are different. The mercury from the end Permian layers doesn't indicate a single, sudden release. In many locations, the sedimentary record shows several pulses of mercury enrichment, a pattern that perfectly mirrors the stop-start, pulsed nature of the Siberian Traps eruptions we see in the lava layers themselves. This creates an incredibly powerful correlation. We have the source, the Siberian Traps, with their millions of cubic miles of magma, known to be rich in volatiles like mercury. We have the signal, the global spike of mercury deposited in rocks of the exact same age, and we have the victim, the fossil record showing mass death happening at precisely the same time. The mercury acts as the perfect chemical bridge, connecting the cause in Siberia directly to the effect felt by every ecosystem on the planet. It's a subtle clue, invisible to the naked eye, but it provides one of the most compelling and direct pieces of evidence that the greatest extinction in Earth's history was indeed born from fire. To understand the true timeline of this disaster, we need a geological clock of extraordinary precision, one that can measure events that unfolded over hundreds of thousands of years with near-perfect accuracy. That clock exists, and it's found in one of the most unassuming and resilient minerals on Earth, zircon. These tiny crystals, often no larger than a grain of sand, are formed in cooling magma and then become trapped within the resulting volcanic rock. While they might seem insignificant, zircons are nature's ultimate time capsules. They have a unique and incredibly useful property. When they crystallize, they readily incorporate atoms of uranium into their structure, but they strongly reject lead. This is the key to everything. Uranium is radioactive and decays into lead at a known, constant rate, a nuclear clock that starts ticking the moment the crystal forms. By very carefully extracting these minuscule zircons from the layered lava flows of the Siberian Traps, and then using advanced mass spectrometers to measure the precise ratio of uranium isotopes to their daughter lead isotopes, geochemists can calculate the exact moment that specific crystals solidified from molten magma. It's a process that requires immense skill and patience, but the results are nothing short of revolutionary. This uranium lead dating method is so precise it can pin down the age of a zircon crystal to within a few tens of thousands of years, even when that crystal is over 250 million years old. This gives us a resolution on deep time that was simply unimaginable just a few decades ago. Applying this technique systematically across the vast expanse of the Siberian Traps has allowed scientists to build a detailed chronological map of the eruptions, transforming a vague concept of a long event into a specific, quantifiable timeline. The data reveals that the main, most devastating phase of this planetary hemorrhage lasted for approximately 900,000 years. That number alone is staggering, but the real story is in the finer details. The eruptions were not a constant, monotonous flow. The zircon ages show clear clusters, indicating distinct, intense pulses of volcanic activity, separated by brief periods of relative quiet. It's as if the Earth was taking a few deep, ragged breaths between catastrophic coughing fits, each new pulse flooding more of Siberia in lava and pumping another massive dose of poison into the skies. The most critical discovery from this zircon detective work is the powerful correlation between these pulses of maximum volcanic fury and the timing of the biological collapse seen in the fossil record. The ages of the zircon crystals from the most voluminous lava flows align almost perfectly with the sharpest declines in global biodiversity recorded in rocks from the same period in places like South Africa and China. This isn't just a coincidence, it's a direct causal link. The uranium lead clocks within these tiny crystals provide the undeniable evidence that the single most intense period of volcanic activity directly triggered the most severe phase of the Great Dying. They tell us that the extinction wasn't caused by the slow creep of environmental change, but by acute, violent shocks to the global system, each volcanic pulse delivering another hammer blow to a world already on its knees. These zircons have given us the murder weapon's exact time of use, forever cementing the Siberian Traps as the primary culprit in history's greatest crime against life. While the tiny zircons give us an incredibly precise timeline of the eruptions themselves, the full global story of the catastrophe is written on a much grander scale in the cliffs, canyons, and quarries of the world. These natural rock exposures, known to geologists as stratigraphic sections, are like the pages of a history book, with each layer of sediment representing a chapter in Earth's story. And on every continent, if you know where to look, you can find the page that marks the end of the Permian period. It's a boundary that is often startlingly obvious, a stark line in the rock that separates a world of abundance from a world of ash and silence. In places like the famous Meishan section in China, which has become a global reference point for this event, you can literally put your finger on the moment everything changed. The rock below the boundary is a pale, fossil-rich limestone, packed with the intricate shells of brachiopods, the coiled forms of ammonoids, and countless other signs of a thriving marine ecosystem. Then there is a distinct dark line, and immediately above it, the rock changes to a dark, often reddish or greenish claystone or shale that is almost completely barren of life. This transition isn't just a local oddity. It's a pattern repeated in rock sequences from the mountains of Italy to the deserts of Iran, from the salt plains of Pakistan to the coastlines of British Columbia. The composition of this boundary clay layer itself is a treasure trove of clues. In many locations, it is rich in tiny particles of volcanic ash. These minuscule shards of glass and crystal were blasted high into the stratosphere by the most explosive phases of the Siberian eruptions, and then carried by global winds before settling gently across the entire planet, forming a thin, persistent rain of dust. Finding this same ash layer with its unique chemical fingerprint that can be matched to the Siberian Traps magma in rocks from opposite sides of the globe is one of the most direct pieces of evidence for the eruption's truly worldwide impact. It's the geological equivalent of finding the same distinct brand of dust on every surface of a crime scene, all pointing back to a single source. In other places, scientists have detected elevated levels of the element iridium within this boundary clay. Iridium is extremely rare in the Earth's crust but is much more common in asteroids and comets. Its presence initially fueled theories of an impact event, much like the one that ended the age of the dinosaurs. However, the iridium anomaly at the Permian-Triassic boundary is generally much smaller and less consistent than the famous Cretaceous-Paleogene layer, leading most scientists to believe it more likely came from the deep mantle material that sourced the Siberian Traps magma, which is also relatively enriched in iridium compared to the surface crust. This illustrates the careful detective work involved. Every clue must be evaluated in context, and sometimes a piece of evidence that seems to point one way can, with further investigation, actually strengthen the case for another. The most powerful aspect of these sedimentary layers isn't just what they're made of, but the story of time they silently tell. That thin, dark boundary layer, which might be only an inch or two thick, represents an immense span of time, perhaps tens of thousands of years. The rate at which sediment accumulates on the deep seafloor is incredibly slow. It's a gradual, patient rain of microscopic plankton shells, dust, and fine clay. The fact that so little material was deposited over such a long period is, in itself, a critical clue. It tells us that the biological productivity of the oceans had crashed catastrophically. With 96% of marine life extinct, there were simply very few organisms left to die, sink to the bottom, and contribute their skeletons to the sediment pile. The seafloor became a place of stagnation, where only the finest particles from the lifeless waters above could slowly settle. Then, as you move upward through the rock layers, you can see the painfully slow process of recovery. The first fossils to reappear are few and far between, often just the hardy, disaster-tolerant species like Lingula, a simple brachiopod that has survived every mass extinction in Earth's history. Gradually, over layers of rock that represent millions of years, the diversity very slowly begins to increase again, but the ecosystems that eventually emerge are completely new, dominated by mollusks like clams and snails and the ancestors of modern corals. By reading the sequence, composition, and thickness of these sedimentary layers, geologists can do more than just date an event. They can reconstruct the pacing of the catastrophe itself, the depth of the biological vacuum it created, and the agonizingly slow tempo of life's return, providing a truly global perspective on an extinction that left no corner of the planet untouched. To understand the true pace of this ancient catastrophe, we turn to a hidden force that has been silently recording Earth's history for billions of years: its magnetic field. Our planet behaves like a giant bar magnet, with a powerful magnetic field generated by the churning of molten iron in its outer core. This field extends far out into space, shielding us from solar radiation and providing the reliable north-south guidance that migrating animals and human navigators have depended on for millennia. But this field is not a constant, unchanging feature. Throughout Earth's deep history, the magnetic poles have wandered across the globe, and even more dramatically, the entire field has completely reversed itself hundreds of times, with magnetic north becoming south and vice versa. These reversals are a fundamental, if unpredictable, part of our planet's behavior, and they leave behind a perfect, invisible time stamp in the rocks themselves. This incredible natural recording process happens when certain iron-rich minerals, like magnetite, are present in molten rock. When lava is liquid and extremely hot, the tiny magnetic minerals within it are free to move and jostle. But as the lava cools and solidifies into rock, usually below a specific temperature known as the Curie point, these minerals suddenly freeze in place. As they solidify, they align themselves perfectly with the direction of Earth's magnetic field at that exact moment in time, like countless microscopic compass needles locking into position. Once set, this magnetic signature remains trapped within the rock, faithfully preserving a record of the magnetic pole's location and the field's polarity, whether it was in a normal state like today or a reversed state, at the precise moment the rock cooled. This field of study, known as paleomagnetism, allows scientists to read this ancient magnetic record, turning volcanic rocks into precise historical documents. When paleomagnetists turned their instruments toward the colossal lava stacks of the Siberian Traps, they were looking for a specific pattern. A volcanic event spanning 1,000,000 years is, to our human perception, an unimaginably long period. But in geological terms, it is actually a very short, rapid episode. The key question was whether the Earth's magnetic field had undergone any reversals during the main eruptive phase. If the traps had been laid down over tens of millions of years, the lava flows would inevitably record several of these full polarity reversals. The layers would show a clear magnetic pattern. Some flows would be locked in a normal polarity, others in a reversed polarity, creating a striped effect through the rock column that would tell a story of a slowly changing world. What the scientists discovered was the complete opposite. The paleomagnetic data from across the entire vast expanse of the Siberian Traps revealed a stunningly consistent signal. Layer after layer of lava, from the bottom of the sequence to the top, all showed the same magnetic alignment. every single one of those frozen compass needles was pointing in the same general direction. This remarkable consistency can mean only one thing. The entire immense volume of lava was erupted and cooled during a single, stable period of Earth's magnetic history. There simply wasn't enough time for a reversal to occur during the main eruptive phase. This finding is a powerful, independent clock that confirms what the Zircon dating had suggested, that this was a geologically rapid event. While 900,000 years feels like an eternity to us, it was merely a blink of an eye in the life of our planet, too short for its restless magnetic field to flip. This paleomagnetic lockstep provides the final, crucial piece of temporal evidence, confirming that the planet was subjected to a concentrated, furious assault of volcanism, a true pulse of geological violence that happened fast enough to overwhelm the world's capacity to cope. Of course, the volcanic narrative is compelling and backed by a mountain of evidence, but in any great scientific mystery, it's crucial to explore every possible suspect. Could an event from the heavens rather than the hellish depths of Earth have been the true trigger for the Great Dying? This is the core of the impact theory, an alternative explanation that has captivated some researchers. The idea itself is powerfully intuitive. We know for a fact that an asteroid impact was the principal cause of the later Cretaceous Paleogene extinction that wiped out the dinosaurs. It's a clean, dramatic, and terrifyingly simple mechanism, a single, instantaneous cataclysm from space that changes the world in a day. So, could a similar celestial bullet have been fired 252 million years earlier? Proponents of this theory have searched long and hard for their own smoking gun, and they've pointed to a few intriguing pieces of potential evidence. For decades, they have investigated several alleged craters that could be of the right age. One of the most discussed is the Araguainha crater in Brazil, a massive impact structure over 25 miles wide. However, detailed dating has shown it to be several million years too old to be the primary culprit for the Permian-Triassic event. Other proposed sites, like the Bedout structure off the coast of Australia, remain highly controversial, with many geologists questioning whether they are truly impact craters at all or just unusual geological formations. Without a clear, massive, and contemporaneous crater, the impact theory lacks its most foundational piece of evidence. The search then turns to more subtle clues, the kind of forensic evidence that a colossal impact would leave scattered across the globe. Impact supporters have pointed to reports of shocked quartz in rocks from the extinction boundary. Quartz crystals subjected to the immense pressure of an impact develop distinctive parallel lines or lamellae under their surface, a clear fingerprint of extreme trauma. They've also looked for traces of iridium, that rare element we mentioned earlier that is far more abundant in asteroids than in the Earth's crust. While there are some minor iridium anomalies from this time, they are nowhere near as pronounced or globally consistent as the layer found at the end of the age of dinosaurs. Furthermore, other telltale signs of a major impact, like widespread tektites, glassy beads of rock vaporized and scattered by the impact, or a definitive layer of impact ejecta, have simply not been found in sufficient quantities across the numerous global boundary sections that geologists have studied. The evidence is at best patchy and open to interpretation. When you weigh this sparse and controversial impact evidence against the overwhelming and consistent case for the Siberian Traps, the scale tips decisively. The volcanic story provides a cause that is not only proven to have happened but also perfectly explains the pattern of the extinction, the million-year duration, the pulses of eruptions matching pulses of extinction, the global mercury spikes, the carbon isotope excursions, and the evidence for prolonged environmental degradation. All of it fits together into a coherent, multi-faceted narrative. An impact is a sudden event. It doesn't easily explain a biological collapse that unfolded over tens of thousands of years. The traps, however, with their long, drawn-out assault on the planet's systems, create exactly the kind of protracted stress that would lead to the complex and staggered extinction pattern we see in the rocks. This ongoing debate is far from just an academic squabble. It highlights a fundamental principle of good science: the rigorous and careful evaluation of all available clues. It forces researchers to sharpen their arguments, to double-check their dates, and to remain open-minded. The current scientific consensus strongly favors the Siberian Traps as the primary driver of the extinction, but the investigation into a potential impact role continues. It's possible that a smaller impact occurred around the same time and added to the world's misery, acting as a final straw that broke the back of ecosystems already reeling from volcanic gases. But as the main suspect, the evidence against the traps is simply too vast, too consistent, and too compelling to ignore. The real story of the Great Dying is not one of a single, sudden blow from space, but of a planet slowly, agonizingly bleeding lava from a wound that refused to heal for 1 million years. The world after the Great Dying was a shattered, hollowed-out place, a planet stripped of its vibrancy and left with only the faintest pulse of life. The silence must have been deafening: vast landscapes of barren rock, empty seas under a hazy, poisoned sky, and a profound absence of the bustling, complex ecosystems that had thrived just 1 million years earlier. This wasn't a world that could simply bounce back overnight. The path to recovery was agonizingly slow, a grueling marathon of evolution that would take an estimated 5 to 10 million years for ecosystems to regain anything resembling their former complexity and stability. This prolonged struggle to rebuild offers us some of the most profound clues about how life on Earth responds to near-total annihilation and the rules for survival in a broken world. The characters in this new, grim drama were not the magnificent giants of the Permian. The winners of this apocalypse were the generalists, the scrappy survivors that possessed a specific set of traits that became priceless in a hostile environment. Size was a major disadvantage. Larger animals require more food and resources, which were now critically scarce. The new rulers were small. Behavior was also key. Creatures that could burrow had a tremendous advantage, able to escape the extreme surface temperatures, hide from increased ultraviolet radiation, and perhaps find dormant plant roots or insects to eat. Think of animals like Lystrosaurus, that humble, beaked herbivore whose fossils suddenly dominate the landscape. It wasn't a champion in the old world, but its ability to dig and its non-picky diet made it a king in the new one. In the oceans, the story was similar. The few survivors were typically organisms that could tolerate low oxygen levels, high acidity, or had planktonic larval stages that could disperse widely to find the few remaining habitable pockets. This period immediately following the extinction is known to paleontologists as the dead zone or the survival phase. The fossil record from this time is heartbreakingly sparse. Ecosystems were simplified to an extreme degree, with very few species doing all the work. There were no complex food webs with multiple levels of predators and prey. Instead, you might have had just 1 or 2 hardy plant species, a single widespread herbivore like Lystrosaurus gobbling them up, and perhaps one small predator trying to hunt it. It was a world operating on a skeleton crew, incredibly vulnerable to any further environmental shocks. This lack of biodiversity meant that ecosystems were fragile and unstable for millions of years, prone to collapse if conditions wavered even slightly. But life, as it always does, began to push back. Very slowly, over millions of years, this survival phase gave way to what scientists call the recovery phase. This wasn't a simple return to how things were. It was a fundamental rebuilding and a dramatic redirection of evolution's course. The empty ecological roles left by the Permian's extinct giants presented an unprecedented opportunity. With little competition, the descendants of those few surviving species began to experiment, to diversify, and to evolve into strange and new forms to fill the vacant niches. This process is known as adaptive radiation, and the post-apocalyptic world was the ultimate breeding ground for it. Small, quick reptiles evolved into new types of predators. Other lineages began to experiment with different body plans and diets, exploring possibilities that had been off-limits when the world was dominated by powerful creatures like the Gorgonopsians. This evolutionary explosion eventually gave rise to the entirely new world of the Triassic period. From those humble, surviving reptiles came the first archosaurs, the group that would eventually produce crocodiles, pterosaurs, and most famously, the dinosaurs. At the same time, the surviving synapsids, our own distant ancestors, also diversified, though they remained mostly small and rodent-like during this time, biding their time in the shadow of the newly emerging rulers. This sets the stage for the entire next act of life on Earth. The Mesozoic era, the age of dinosaurs, was not a separate story. It was a direct consequence of the vacuum created by the Great Dying. The Permian extinction didn't just kill off the old guard. It forcibly cleared the stage, allowing a whole new cast of characters to make their entrance. The resilience on display here is not about strength or ferocity, but about adaptability and the relentless, patient pressure of evolution to exploit any available opportunity, no matter how slim. The recovery shows us that even from the very brink of nothingness, life can not only return but can reinvent itself in astonishingly creative ways. While the story of the Siberian Traps is almost too colossal to fully grasp, we don't have to look back 252 million years to see these destructive processes in action. We can observe smaller, yet incredibly instructive, examples happening right now. Modern volcanic activity provides us with a living laboratory, a scaled-down preview of the kinds of forces that devastated the Permian world. By studying these contemporary events, scientists can test their models, validate their theories, and gain a much clearer understanding of how a planet's systems respond to a volcanic shock. The past may hold the clues, but the present gives us the key to interpreting them. A perfect case study is the 1991 eruption of Mount Pinatubo in the Philippines. This was not a quiet lava flow. It was a violent, explosive eruption that shot a colossal column of ash and gas over 22 miles high, directly into the stratosphere. The most significant aspect of Pinatubo wasn't the lava or the ash that buried the surrounding countryside, but the immense volume of sulfur dioxide it injected into the upper atmosphere, an estimated 20 million tons of it. Up there, that sulfur dioxide gas quickly reacted with water vapor to form a hazy layer of microscopic sulfuric acid aerosols. This veil of tiny particles did something remarkable. It acted like a giant planetary sunshade. For the next 2 years, this aerosol cloud circulated the globe, reflecting a significant amount of incoming sunlight back into space. The result was a measurable global cooling effect. The Earth's average temperature dropped by about 1 degree Fahrenheit for nearly 2 years following the eruption. This might not sound like much, but it was a powerful demonstration of a volcano's ability to temporarily alter the global climate. It was a real-time, observable example of the kind of atmospheric chemistry that, on a much smaller scale, mimics the initial cooling effect scientists believe may have occurred at the very start of the Siberian Traps eruptions before the overwhelming greenhouse warming took hold. But Pinatubo also taught us about the other side of the coin, the recovery. After about 2 years, those sulfate aerosols eventually fell out of the atmosphere and the cooling effect dissipated. The system returned to its pre-eruption state. This highlights a critical difference between a short-lived explosive event like Pinatubo and a prolonged flood basalt eruption like the Siberian Traps. Pinatubo was a single, sharp punch to the climate system from which the planet could recover relatively quickly. The traps, however, were a million-year-long beating. They wouldn't have allowed for any recovery. Just as one pulse of aerosols might have started to clear, another enormous eruption would have pumped the atmosphere full of yet more gas and ash, creating a relentless, unsustainable stress on the global climate system. The modern analog shows us the mechanism, but it also underscores the unimaginable scale and duration required to push the planet past a point of no return. For a different perspective, we can look to the ongoing volcanic activity in Iceland. This is less about explosive, climate-altering eruptions and more about the kind of persistent, effusive lava flows that characterize the Siberian Traps, albeit on a much smaller scale. Iceland sits directly atop the mid-Atlantic ridge, a divergent tectonic plate boundary, and also over a deep-seated mantle plume, making it one of the most volcanically active places on Earth. Eruptions like the one from the Hellorheim fissure in 2014-2015 provided a fascinating modern glimpse into the type of gas emission that would have been so devastating during the Permian. The Hellorheim eruption was a classic flood basalt event. It wasn't particularly explosive, but it produced a massive, slow-moving river of lava over the course of 6 months. Most importantly, it released a staggering amount of sulfur dioxide gas, up to 60,000 tons per day at its peak. For months, this constant, powerful emission created significant air quality problems across Iceland and even detectable pollution as far away as Western Europe. Studying an event like Hellorheim allows scientists to directly measure the chemistry and volume of gases being released from a fissure eruption over time. They can track how these gases disperse in the atmosphere, how they interact with sunlight and other compounds, and what their immediate effects are on local environments. This data is invaluable for building and refining computer models that simulate the atmospheric effects of the Siberian Traps. If we know how much so too a single Icelandic fissure emits over 6 months, we can start to more accurately estimate the mind-boggling consequences of thousands of such fissures, all erupting in pulses for a million years. These modern events are the Rosetta Stone that helps us translate the ancient chemical fingerprints locked in Permian rocks into a dynamic, terrifying story of atmospheric poisoning. They provide the crucial link between the silent, stone evidence of the past and the noisy, observable science of the present, reminding us that the forces that reshaped our planet are not extinct. They are merely dormant, and studying their modern whispers is essential to understanding their ancient screams. The story of the Great Dying is far from a closed book gathering dust on a shelf. It is a dynamic, evolving field of science where every passing year brings new revelations that challenge our understanding and paint an ever clearer picture of this ancient apocalypse. The detective work continues at a breathtaking pace, powered by technological advancements that would have been the stuff of science fiction just a few decades ago. We are no longer limited to just hammers and chisels. Today's paleontologists and geochemists wield an arsenal of tools that allow them to interrogate the rocks with unprecedented precision, extracting secrets that were once thought to be lost to deep time forever. One of the most significant leaps forward has been in the realm of radiometric dating. The uranium lead dating of zircon crystals we discussed is becoming even more refined. New generations of mass spectrometers are so sensitive they can analyze individual zircon grains that are smaller than a speck of dust, allowing scientists to date volcanic ash layers with an error margin of just a few thousand years, even at a distance of 252 million years. This incredible precision is helping to resolve long-standing debates about the sequence of events. For instance, recent high-resolution dating from sites in China suggests that the most severe pulse of the marine extinction might have occurred shockingly fast, perhaps in as little as 30,000 years, and that it was preceded by a smaller, earlier pulse of extinction on land. This refined timeline is crucial because it helps scientists determine the exact kill mechanisms. If the extinction was geologically instantaneous, it might point toward a single catastrophic trigger. But if it was staggered, with terrestrial life succumbing before marine life, it better supports a prolonged, multi-pronged assault from volcanism, which is exactly what the latest data seems to show, perfectly aligning with the pulsed nature of the Siberian eruptions. Beyond dating, satellite imaging and advanced geophysical techniques are giving us a completely new perspective on the Siberian Traps themselves. This region is remote, vast, and incredibly difficult to study on the ground. But from space, satellites equipped with radar and gravity mapping instruments can peer beneath the surface vegetation and soil to map the three-dimensional structure of the lava flows hidden below. These surveys have revealed that the volume of volcanic rock might be even greater than previously estimated, with massive, previously unknown intrusions called sills snaking deep into the ancient crust. These sills are just as important as the surface lava flows. As these tongues of magma baked the surrounding rock, they would have cooked vast deposits of coal, salt, and organic-rich shale, releasing additional enormous volumes of greenhouse gases like carbon dioxide and methane directly into the atmosphere and groundwater without ever breaking the surface. This discovery has forced a major revision of the total gas budget for the event, suggesting that these subterranean gas factories may have been just as significant as the gases released by the eruptions we can see, adding a powerful new dimension to the model of atmospheric poisoning. Meanwhile, in laboratories around the world, climate modelers are feeding all this new geological data. The refined timelines, the updated gas volumes, the new sources of carbon into immensely powerful supercomputers. These are not simple models, they are complex virtual worlds that simulate the physics, chemistry, and biology of the entire planet. Researchers can now run sophisticated experiments, tweaking one variable at a time to see its effect. What happens if we double the amount of sulfur dioxide? How does the ocean circulation change if the temperature rises by 8 degrees instead of 10? The results have been startling. Recent models indicate that the ozone layer destruction may have been even more severe than thought, and that the resulting burst of ultraviolet radiation could have been a primary driver for the extinction on land, stunting plant growth and causing widespread genetic damage. Other models are successfully simulating the exact patterns of ocean acidification and anoxia that we see evidenced in the rocks, confirming that the sequence of events, warming leading to stagnant oceans leading to suffocation, is not just plausible but inevitable given the scale of the volcanic forcing. And the fossil evidence continues to mount, often from unexpected places. New fossil sites are being discovered that capture the extinction interval in exquisite detail. In Norway, for example, a section of rock has been found that preserves a continuous record of marine life from the late Permian right through the early Triassic. The fossils here show not just which animals disappeared, but how they suffered in the lead up to their demise. Scientists are finding evidence of Lilliput effects, where surviving species are dramatically smaller than their ancestors, a classic sign of environmental stress. They are also finding malformed shells and bones from the period right before the collapse, direct physical evidence of organisms struggling to grow in increasingly acidic and oxygen-poor conditions. Each of these tiny fossils is a snapshot from the front lines of the catastrophe, providing a biological corroboration of the chemical and physical story told by the rocks. This ongoing research is a beautiful reminder that science is a self-correcting, ever-evolving process. Each new technique, each fresh discovery, is like turning up the resolution on a blurry photograph. The broad outlines of the Great Dying have been clear for some time. A massive volcanic eruption caused a global environmental collapse, but the details are now coming into stunning focus. We are moving from knowing what happened to understanding exactly how it happened, the precise sequence of cause and effect that took a thriving world and brought it to the very brink of barrenness. The mystery is certainly not solved. Every answered question seems to spawn two new ones, but with the powerful tools now at our disposal, we are piecing together the most complete and terrifying narrative of planetary collapse ever assembled, one that holds profound lessons for our own world today. But as if the direct volcanic emissions weren't enough to push the planet into chaos, there's a compelling and terrifying possibility that the Siberian Traps didn't just poison the world on their own. They may have triggered a sleeping giant lurking in the ocean's depths, unleashing a feedback loop that sent the crisis spiraling completely out of control. This giant is methane hydrate, a strange, ice-like substance that exists in a fragile equilibrium at the bottom of cold, high-pressure oceans. Methane hydrates, also known as clathrates, are essentially cages of frozen water molecules that trap immense quantities of methane gas inside them. They form naturally from the decay of organic matter on the seafloor, and under the right conditions of low temperature and high pressure, they remain stable, locking away a colossal reservoir of carbon. In fact, the total amount of carbon stored in global methane hydrate deposits today is estimated to be truly staggering, potentially double the amount of carbon in all known fossil fuel reserves on Earth. This vast reservoir represents a latent, frozen bomb of greenhouse gas, and 252 million years ago, the volcanic fires of Siberia may have provided the perfect spark to set it off. The proposed chain of events is as frightening as it is straightforward. The initial pulses of volcanic eruptions began pumping enormous volumes of carbon dioxide and sulfur dioxide into the atmosphere, kickstarting a significant greenhouse warming effect. As global average temperatures began to climb, this warming didn't just affect the land and the air, it slowly but surely penetrated into the world's oceans. Deep ocean currents over centuries and millennia would have carried this warmth down to the seafloor, particularly in the shallow continental shelves where vast deposits of methane hydrates are most common. For these ice-like structures, temperature is everything. They exist in a very narrow window of stability. Even a slight increase in the temperature of the surrounding water can be enough to disrupt that delicate balance, causing the solid hydrate structure to break down and dissociate. In a process akin to opening a shaken soda bottle, the once solid lattice would have fizzed and fractured, releasing the trapped methane gas as billions of bubbles rising through the water column to erupt into the atmosphere above. The consequences of such a release would have been nothing short of catastrophic. Methane is a greenhouse gas that is, molecule for molecule, vastly more powerful than carbon dioxide. Over a 100-year timescale, it is about 28 times more effective at trapping heat in the atmosphere. A massive, rapid release of methane from the ocean floor would have acted like throwing jet fuel on the already raging fire of volcanic warming. This sudden infusion of an ultra-potent greenhouse gas would have dramatically accelerated the rate of global temperature rise, potentially pushing the climate system past a critical threshold or tipping point from which there was no return. This is the nightmare scenario, the initial volcanic warming triggering a secondary, even more powerful pulse of greenhouse gas that the planet itself had been storing, creating a vicious, self-reinforcing cycle of heat that would have made the environmental collapse even more severe and irreversible. The most compelling evidence for this theory comes from the same carbon isotope records we discussed earlier. You'll recall that the volcanic gases from the mantle were rich in light carbon, carbon-12, which caused a strong negative shift in the global carbon isotope ratio. However, methane from hydrates is also extremely depleted in the heavy carbon-13 isotope. In fact, it's even lighter than volcanic carbon. Some scientists argue that the massive negative swing seen in the rocks is simply too large to be explained by volcanic emissions alone. They point to the shape of the isotopic curve, which shows a very sharp, steep decline right at the extinction boundary. This rapid plunge, they suggest, is the chemical signature of a gigantic, geologically instantaneous burp of incredibly light methane carbon suddenly flooding the atmosphere and oceans, superimposed on top of the more gradual release from the volcanoes. It's the difference between a steady drip and a sudden flood, both from the same source of light carbon, and the isotopic record seems to capture that flood perfectly. Furthermore, sophisticated climate models that simulate the effects of such a large methane release produce results that are chillingly consistent with the severity of the extinction. The models show that this kind of event could produce the extreme, rapid warming and the corresponding ocean acidification, as methane oxidizes in the atmosphere to form CO2 that the geologic evidence demands. It provides a plausible mechanism to explain how the environmental changes could have been so fast and so devastating, pushing global temperatures to those lethal highs of 10 degrees Celsius or more in a relatively short time frame. However, this methane hydrate gun hypothesis is not without its critics and remains an active area of debate. Some geochemists argue that the carbon isotope excursion can be fully explained by the sheer volume of carbon released from the Siberian Traps themselves, especially when you account for the baking of coal and organic-rich sediments by underground magma intrusions, which would also release light carbon. Others question whether the ocean warming, transmitted slowly from the surface to the depths, could have been rapid and uniform enough to destabilize hydrates across the globe simultaneously to cause the required catastrophic release. The search for more direct physical evidence of a massive hydrate dissociation event, such as specific sedimentary structures on the ancient seafloor formed by large-scale methane escape, has so far been inconclusive. This scientific debate is crucial because it gets to the very heart of how planetary systems operate under extreme stress. Whether the methane hydrates were a primary player or a minor contributor, their proposed role highlights a fundamental and frightening truth about our planet. Its systems are deeply interconnected. An event on one part of the globe can unlock feedback mechanisms that dramatically amplify the initial problem. The story of the Great Dying may not be just one of a planet being attacked from the outside by volcanoes, but also one of it being betrayed from within, its own ancient carbon reserves turning against it in a final, devastating blow. In the aftermath of such overwhelming devastation, survival was not a matter of strength or ferocity, but of pure, unadulterated adaptability. The rules of the game had been completely rewritten by the volcanic chaos, and the organisms that made it through were those that possessed a very specific, almost humble set of advantages. This was the ultimate test of Darwin's principle, not in a slow, competitive grind, but in a sudden, brutal filtering event. The fossil record from the early Triassic period shows us that the winners of this apocalypse were rarely the giants or the specialists. Instead, they were the generalists, the unassuming creatures whose simple traits became priceless keys to survival in a world turned hostile. Consider the profound advantage of being small. In a landscape where food webs had utterly collapsed and resources were desperately scarce, a large body was a fatal liability. Big animals require vast amounts of food and water to sustain their metabolism. The magnificent plesiosaurs, the size of small cars, and the powerful, saber-toothed gorgonopsians simply couldn't find enough to eat in the barren, acid-scorched world. Their size, once a symbol of dominance, became a death sentence. In stark contrast, smaller animals needed far less sustenance to survive. A creature the size of a modern rat could subsist on seeds, insects, or decaying plant matter that would be inconsequential to a larger predator. This simple fact of biology is written plainly in the rocks. The fossils that appear immediately after the extinction boundary are almost universally from species that were significantly smaller than their pre-extinction ancestors, a phenomenon paleontologists call the Lilliput effect. But size alone wasn't enough. Behavior was perhaps an even more critical factor. The ability to burrow became one of the most powerful survival strategies on the Permian-Triassic frontier. A burrow offered a portable sanctuary from the hellish conditions on the surface. It was a shelter from the extreme temperature swings, a hiding place from the increased ultraviolet radiation piercing the weakened ozone layer, and a cool, damp refuge from the scorching heat and acid rain. For an animal that could dig, the entire world wasn't lost. It still had its own little pocket of relative safety. This is why we find so many fossils of burrowing animals from this time. Creatures like Thrinaxodon, a small, dog-sized cynodont that was a distant relative of mammals, are often found curled up in fossilized burrow casts, preserving a poignant snapshot of an animal hunkering down to wait out the worst of the catastrophe. Their anatomy gives them away strong forelimbs, sturdy claws, and a compact body shape perfect for a subterranean lifestyle. And then there's the story of diet. The specialized predator that only ate one type of reptile, or the herbivore that relied solely on a particular species of fern, was doomed when their specific food source vanished. The survivors were the ultimate opportunists, the biological equivalent of culinary omnivores who could stomach whatever was available. A broad, non-selective diet was a passport to continued existence. These animals could switch from eating tough, leathery surviving plants to scavenging carcasses, to digging up roots or catching the few remaining insects. This flexibility allowed them to exploit every last calorie in an otherwise empty world, giving them a crucial edge over their pickier contemporaries. No single creature embodies this perfect storm of survival traits better than Lystrosaurus. This animal was, by all accounts, not particularly impressive. About the size of a modern pig, it was a stout, squat herbivore with a pair of stubby tusks and a turtle-like beak for cropping vegetation. Before the extinction, it was a minor, almost background player in the rich ecosystems of Pangea. But when the cataclysm struck, its mundane traits became superpowers. Lystrosaurus was the right size, not too big, not too small. Evidence suggests it was likely a burrower, capable of escaping the harsh surface conditions. And its beak indicates a generalist diet. It could probably eat a wide variety of tough, low-quality plants that sprouted in the damaged soils. As a result, Lystrosaurus didn't just survive, it absolutely exploded across the entire supercontinent. In some fossil assemblages from the early Triassic, its bones make up an astonishing 95% of all vertebrate fossils. It became, for a brief period, the most successful animal on the planet, a testament to the idea that in a world turned upside down, it's not the strongest or the fiercest who inherit the Earth, but the most adaptable. Its story, written in countless bones, is one of the most powerful clues we have about the harsh realities of life after the apocalypse and the simple, humble qualities it takes to endure. And so, the world that emerged from the ashes of the Great Dying was not merely a scarred version of the old one. It was an entirely new stage set for a completely different evolutionary play. The Permian-Triassic extinction did far more than just wipe the slate clean. It shattered the slate, melted down the pieces, and forged an entirely new one from the molten remains. This wasn't a simple interruption. It was a hard reset for the entire course of life on Earth, a violent pivot point that redirected the flow of evolution for the next 200 million years and ultimately made our own existence possible. The legacy of that million-year hemorrhage of lava is not a fossilized relic of a distant past. It is woven into the very DNA of the modern world, from the continents we walk on to the air we breathe. Before the catastrophe, the world was dominated by the ancestors of mammals, the synapsids. Creatures like the formidable Gorgonopsians and the bulky Periosaurs were the undisputed rulers of Pangea, and they were on an evolutionary trajectory all their own. Had they continued, the planet might be populated today by their bizarre and alien descendants. But the Great Dying acted like a brutal filter, and it was the reptiles, a group that had been relatively marginal during the Permian, that found themselves holding the winning ticket. In the empty, broken world of the early Triassic, these reptiles possessed the right combination of traits, often smaller size, faster metabolisms, and different reproductive strategies, that allowed them to adapt and diversify with breathtaking speed into the ecological voids left by the extinct giants. From this humble beginning, a new group emerged, the Archosaurs, the ruling reptiles. And from the Archosaurs would spring every incredible creature we associate with the age of dinosaurs: the towering sauropods, the terrifying tyrannosaurs, and the soaring pterosaurs. For over 150 million years, dinosaurs would become the most successful land animals on the planet, a reign of terror and wonder that was made possible only because the volcanic fires of Siberia had cleared the way. But the story doesn't end with the dinosaurs. Our own lineage, the mammals, also owes its existence to this same catastrophe. The few synapsids that did survive, small, burrowing, shrew-like creatures, were forced into the shadows. They became nocturnal insectivores, living in the literal and figurative shadow of the new dinosaurian giants. This period of forced humility and isolation was, paradoxically, a crucible for innovation. To survive in a world dominated by dinosaurs, these early mammals had to evolve. They developed fur for insulation, a more efficient four-chambered heart, and a unique jaw structure that would eventually allow for a wide variety of diets. Most importantly, they evolved increasingly large and complex brains to navigate their dangerous world. They were the underdogs biding their time. When another asteroid impact ended the dinosaurs' reign 66 million years ago, it was these small, smart, adaptable mammals that were perfectly poised to explode into the vacated niches, eventually giving rise to every mammal on Earth today, from bats to whales to us. The human story, with all its complexity, began with a handful of lucky survivors scrambling in the darkness after the planet's worst day. Beyond the biological revolution, the physical legacy of the Siberian Traps is literally set in stone. The unimaginable volume of lava and underground magma intrusions didn't just spew gas. They fundamentally altered the geology of the planet. As those colossal bodies of magma cooled slowly underground, they created some of the largest and most valuable mineral deposits on Earth. The Norilsk region in Siberia, the very heart of the traps, is one of the most mineral-rich places on the planet, containing gigantic reserves of nickel, copper, palladium, and platinum. These metals are essential to modern industry and technology, from stainless steel to catalytic converters to the batteries in our phones and electric cars. Our technological civilization is, in a very real sense, built upon the metallic bounty produced by that ancient cataclysm. Furthermore, the weathering of all that new volcanic rock over millions of years released a slow, steady stream of nutrients like phosphorus and calcium into the oceans, helping to eventually re-fertilize the marine environments and set the stage for the return of healthy ecosystems. This event even left a permanent mark on our atmosphere. While the CO2 levels eventually stabilized, the planet remained in a greenhouse state for millions of years, and some scientists argue that the event set a new, warmer baseline for the entire Mesozoic era. This deep time perspective offers a profound and humbling lesson. The Permian-Triassic event reminds us that the Earth is not a static, stable stage upon which life plays out its drama. It is a dynamic, powerful, and occasionally violent participant. The planet's immense geological forces have the power to create and destroy on a scale that dwarfs human comprehension, redirecting the river of evolution with casual, brutal force. The legacy of that million-year eruption is all around us. It's in the very fact that we exist to ponder it, in the minerals we pull from the Earth to power our societies, and in the ancient rocks that tell a story of resilience against impossible odds. It is a permanent reminder that change is the only constant in the history of our planet, and that from the most profound destruction can emerge the most unexpected and brilliant forms of new life. To truly grasp the full, terrifying scope of the Great Dying, we must move beyond the individual clues and learn to see the planet as a single, interconnected system pushed past its breaking point. This is where the power of modern science truly shines, through the use of sophisticated theoretical computer models. Think of these not as simple video game simulations, but as incredibly complex virtual worlds, built on the fundamental laws of physics, chemistry, and biology. Scientists can feed all the disparate pieces of evidence we've discussed: the volume of the lava flows, the chemistry of the gases, the isotopic shifts in the rocks, the fossil record of extinction into these digital laboratories. The goal is breathtakingly ambitious: to reanimate the catastrophe, to watch it unfold in accelerated time, and to test whether our proposed sequence of events could actually produce the devastated world we find in the geological record. The process begins with the initial conditions. Researchers program the model with a realistic Permian world, the configuration of the Pangea supercontinent, the depth and chemistry of the oceans, the composition of the atmosphere, and the state of the primitive sun. Then they introduce the villain, the Siberian Traps, but they don't just add a generic volcano. They input data based on the Zircon dating, specifying that the eruptions occurred in distinct, powerful pulses over 900,000 years. They calculate the trillions of tons of carbon dioxide, sulfur dioxide, and methane based on the volume of the lava and the baking of underground coal and limestone by magma intrusions. With everything set, they press play, and the model begins to calculate the consequences, hour by virtual hour, year by virtual year, across the entire globe. What these simulations reveal is the terrifying power of cascading effects and feedback loops. The models show that the initial volcanic CO2 would have begun warming the planet steadily. But then, other processes kick in, amplifying the heat in a vicious cycle. For example, as the model's polar ice caps melt, as we know they did, it doesn't just raise sea levels. The loss of bright, white ice means the planet's surface absorbs more of the sun's energy instead of reflecting it back into space, an effect known as ice albedo feedback, which causes even more warming. The models can also simulate the proposed methane hydrate release. As the virtual oceans warm, the program calculates the point at which these frozen deposits would destabilize, adding a massive new pulse of potent greenhouse gas that sends the global temperature rocketing upwards at an even steeper rate, perfectly matching the sudden plunge in carbon isotopes we see in the rocks. Perhaps the most valuable role of these models is their ability to quantify the disaster, to move us from qualitative descriptions like "it got very hot" to terrifyingly precise numbers. The most advanced climate models consistently show that the combination of volcanic CO2 and potential methane release could drive average global temperatures up by around 10 degrees Celsius. To put that number into a modern context, that is more than 10 times the amount of warming our planet has experienced since the last ice age ended. The models also calculate the resulting ocean acidification, predicting a drop in oceanic pH that would have been lethal to most shell-building organisms, and they map the spread of anoxic dead zones as ocean circulation grinds to a halt. The incredible part is that these model predictions aren't just abstract numbers, they are validated by the hard evidence, the temperature proxies from oxygen isotopes, the evidence of shell dissolution in the rocks, and the pyrite layers indicating suffocation all align stunningly well with the model's output. This agreement between the virtual world and the real, physical evidence is what gives scientists such strong confidence in the overall narrative. These models are also invaluable for testing alternative theories and understanding nuances. For instance, researchers can run an experiment where they only include the sulfur dioxide from the eruptions. The model might show a brief period of global cooling from the sun blocking aerosols, which could explain some of the more complex patterns seen in the fossil record, where some ecosystems might have been hit by cold before the overwhelming heat arrived. They can tweak the amount of gas released from the underground coal baking versus the surface eruptions to see which scenario best matches the global carbon isotope curve. In this way, theoretical modeling isn't a closed book. It's an active, dynamic tool for interrogation. It allows scientists to ask "what if" and get a quantitative answer, refining our story of the great dying from a rough sketch into an increasingly detailed and horrifyingly precise picture of how a planet can die, and how, against all odds, it can eventually begin to heal. Despite the mountain of evidence we've pieced together, the story of the great dying is far from complete. In many ways, the more we learn, the more we realize just how much remains shrouded mystery. These lingering questions aren't signs of failure. They are the very engines of scientific discovery, driving geologists, paleontologists, and climate scientists back into the field and the laboratory year after year. The case of the Permian-Triassic extinction is still very much open, and some of its most fundamental mysteries continue to defy easy answers. One of the most perplexing puzzles is the sheer duration of the eruptions. Why did the planetary hemorrhage persist for nearly 1 million years? A mantle plume surging from the deep Earth is a powerful force, but even the most massive plumes tend to release their energy over a shorter, more intense period. The Siberian Traps stop-start pattern over such an immense timescale suggests something more complex was at work. Some leading theories propose that the geology of the Siberian crust itself was uniquely suited to prolong the agony. Perhaps the continental rock was particularly rich in fusible minerals that kept generating new magma as the heat from the plumes soaked in. Or maybe the tectonic stress field across Pangea was perfectly aligned to keep the crust fractured and open, acting like a release valve that couldn't be shut, allowing magma to bleed out slowly instead of erupting in a few catastrophic explosions. Unraveling this mystery requires not just looking at the lava itself, but reconstructing the ancient crust that it tore through, a monumental geological detective job. Then there's the complex dance of death between the volcanic gases and the global climate. We have a broad brush understanding. Carbon dioxide warmed the planet, sulfur dioxide caused cooling and acid rain, and halocarbons destroyed the ozone. But the precise timing, quantity, and interaction of these gases remain a subject of intense debate. Sophisticated climate models are our best tool here, but they rely on accurate inputs. Did the eruptions release these gases in a steady stream or in violent, concentrated pulses? How much of the carbon dioxide came directly from the magma, and how much was secondary, released from baked coal seams and limestone by the underground magma intrusions? The answer dramatically changes the narrative. A sudden, massive pulse of gas could cause a much faster climate shock than a slow trickle, potentially explaining why some species seem to disappear from the fossil record more abruptly than others. Pinpointing the exact sequence is like trying to reconstruct the precise order of events in a multi-car pileup from the final wreckage. Every detail changes the story of cause and effect. This leads directly to perhaps the biggest question of all. Were the Siberian Traps the sole killer, or did they have accomplices? The evidence for a single, massive asteroid impact is weak, but that doesn't rule out other contributing factors. Could a period of intense volcanism have made the planet more vulnerable to a smaller, yet still significant, impact from space? Some researchers point to faint clues in the rock record, like slightly elevated levels of the element iridium and rare microscopic structures that could be shocked minerals, and argue that we shouldn't dismiss the idea entirely. Other potential accomplices are even more subtle. Was Earth's magnetic field unusually weak or unstable at the time, allowing more harmful solar radiation to reach the surface and adding another stressor to life? Could a series of powerful earthquakes triggered by the doming crust have released large amounts of methane from terrestrial reservoirs, adding to the greenhouse gas burden? Each of these possibilities is a thread that scientists are carefully pulling on, knowing that the story of the planet's worst day might be even more complex than we ever imagined. These aren't just academic questions, they are crucial for understanding the limits of life's resilience and the fragility of our own planet's systems. Every new expedition to the remote reaches of Siberia, every new analysis of ancient rock samples with ever more sensitive instruments, and every new run of a supercomputer climate model brings us a little closer to answers. The investigation continues, ensuring that the final chapter on the Great Dying has not yet been written. Each discovery adds a new piece to the puzzle, reminding us that the most compelling stories from Earth's deep past are those that are still being unearthed, one rock hammer tap at a time. The story of our planet's greatest catastrophe is far more than a tale of ancient destruction. It is a profound lesson in resilience, interconnectedness, and the incredible power of curiosity. For hundreds of millions of years, the evidence of this event lay hidden, locked away in layers of stone and the silent testimony of fossils, waiting for us to learn how to read it. And what we've discovered should leave us in awe. The Earth is a dynamic, living system, capable of both nurturing life with breathtaking generosity and unleashing forces of almost unimaginable power that can bring it all to the brink. The Siberian Traps weren't just a volcano, they were a planetary fever, a symptom of a deeply interconnected world where a change in one part of the system can trigger a cascade of consequences that reverberates across the entire globe. This ancient drama holds up a mirror to our own time. While we are not facing a million-year volcanic eruption, we are conducting our own unprecedented experiment with the planet's atmosphere and oceans by releasing vast quantities of greenhouse gases. The clues from the Great Dying, the rapid warming, the ocean acidification, the spreading dead zones are not just historical footnotes. They are a warning written in stone, a demonstration of how sensitive and fragile Earth's life support systems can be when pushed too far, too fast. Understanding this past isn't about dwelling on doom, it's about empowerment. It gives us the knowledge to see the potential consequences of our actions and the urgency to chart a wiser course. The past provides the context, but the future is still ours to write. This incredible detective story, pieced together from zircon crystals and fossilized burrows, from mercury spikes and carbon isotopes, is a testament to human ingenuity and our relentless desire to understand the world around us. It's a reminder that by asking questions, by carefully gathering evidence, and by working together across scientific disciplines, we can unravel mysteries that are hundreds of millions of years old. We've managed to reconstruct the story of a planet on fire from the faintest of chemical whispers and the most subtle patterns in rock. If we can accomplish that, it gives us hope that we can also understand and address the complex challenges we face today. Thank you for joining this incredible journey back in time to witness one of history's most pivotal moments. If you found this exploration of our planet's deep past as fascinating as we do, please consider subscribing for more adventures into the greatest mysteries of history and